Okay, so our next speaker is Łukasz Langa. He has used to work in the biggest Polish e-commerce platform, Allegro, now working for Facebook in California. Łukasz will talk about concurrency and explain us why Facebook uses Python 3. Call me later, Łukasz Langa.
Hello, I'm Łukasz. I'm from the internet. You can find me in those multiple places and here at the venue for the next 2 days. So come talk to me about like everything. We can rant about Facebook, Python 3, type hints, cycling, whatever. I love to talk to people. So async. Facebook loves async. PyWaw Summit loves async. I heard that that's going to be the next big thing. I don't think it's going to be. I know it's going to be because we already include it as one of the core features of the sort of PHP evolution we use for Facebook.com, the app. So we already use it heavily. Even in C++, there's this open source library we have, which is like immensely popular. And one of the biggest points about it is that it's mostly async. It introduces async APIs where most of the time people using C++ would think of using blocking APIs. Moreover, we have this embedded persistent key value store that we open sourced, and the API by default is async as well, and it's the most growing MySQL backend now that's using RocksDB. So I mean, yeah, like we know that async is cool, but why? Why is async cool? So the typical answer to that would be that you tend to have a workload that consists of multiple things to be done, but ultimately it yields one result, like rendering a page. So if you only could sort of do some of those steps concurrently, the time required to render the page is going to be shorter, so everybody's going to be happy. Moreover, you know, it improves responsiveness, because if the thing that you're waiting for is not the database but the user, you can do like multiple things in the so-called background. So all the sorts of things like communicating with the network, progress bars, you know, waiting for the mouse click, whatnot, everything like that, concurrency. So the typical answer, you know, you maybe learned during your courses at university or whatnot is, let's use threads, right? Threads are cool, you know, IPC, this sort of thing, but practice shows that it's not really such a clearly cut answer. It makes debugging hard, and I mean, realistically, there are problems that you only ever have in production, so how do you even approach debugging them? Like it's hard because shared state is hard. And moreover, it needs locks, lots and lots of locks, which is why that's like one of the most tricky courses at university, locks, you know, operating systems, this sort of thing. Moreover, Marc-Andre already told you that, well, in Python, threads don't really yield that much of a gain in performance because we have this global interpreter lock, which means concurrency is still pretty bad. If you wait on a network, we can cheat a little, so it's fine, but as soon as you start doing sort of, you know, computational heavy workloads, you'll see that it doesn't really give you anything to have multiple threads. So all in all, they are underutilized. So if we only could, you know, put more work into this single thread, we would already have better performance. Then you can just run multiple processes and you're done. So suddenly we have a solution. We only have to have something that will make the single thread do more work without blocking. So even before PEP 8, I don't know if many of you remember this time, but there was a time where there wasn't PEP 8 yet. There were like those genius programmers using Python already, and one of them was Glyph, and he came up with Twisted, this sort of batteries included for the internet, and it's async heavy. It's a radically different and cleaner approach to do network programming. At the time, Guido was sort of busy with, you know, moving to the US, adding nested scopes to Python 2.1, unit tests and the warnings framework were also introduced at this time. That was predating even new style classes, so that was, ancient times. So it took only another like 7 years for Greg Irving to come up with PEP 380 and for Camellia to, pop up, showing, hey, we can actually do asynchronous programming using generators. We can sort of enhance generators and use them to be sort of a cleaner syntax for what Twisted does with deferreds. People hear deferreds and they get scared. So it took another few years for Async IO to appear, which is the work of Guido van Rossum with, lots of help from Victor Stinner, Glyph himself, and Lorenz van Houtven, my dear friend who until recently lived in Krakow. So what is Async IO? There is a very simple answer, which I can put in one sentence, I think. It's an event loop. What the event loop does is, it's a loop, and in every iteration, it only ever calls a single callback. That's what it does. It's very simple. How do you use the event loop? Well, you get it and you run it forever. Disclaimer, all the code is Python 3, naturally. So yeah, you get the event loop. Why would you do that? Because there might be multiple event loops if you have multiple threads. Or maybe you have a special event loop for your unit tests, obviously. So yeah, you get the event loop, you run it forever. What does it mean that you run it forever? I already told you. Basically, you run forever, you loop, and during each loop, you just run once, doing some magic that selects which callback should be run now, but that's basically it. So what does the loop call? How do you register callbacks to be executed? That's also very easy. There are multiple ways to do that. Well, two of them would be call later and call soon. Call later means wait at least this time, which in the example is 2 seconds, and run the function that is there. It's just a simple function, whatever. Or you can say call soon, which means as soon as you're done with the current stuff that you already have scheduled, just run this thing too. So in this particular example, what we will get is poof. 3 things were, ran, Python stopped executing, we're all happy. So in our graph kind of world, we see that, we execute anything 1, anything 2, anything 3, then we wait for those 2 seconds. For those of you not familiar with select, that basically means we are not like busy looping, not doing anything. We're just sort of giving that responsibility to the operating system. And once the event, passes, we can stop the loop and we are done. But this assumes that every event loop iteration, so every callback, is like really short. It takes just a little amount of time for it to be executed. Because when it's not, when anything is really slow, then you see that everything that is scheduled to be executed afterwards has to wait for it. So you're back in the blocking world, nobody's happy, it's very, very slow. But Async IO is helpful. Async IO will tell you that this callback sucks. You need to sort of, come up with a better way of solving your problem. If you run with Python Async IO debug, it'll tell you, hey, that callback took 1 second, shame on you, or 2 seconds or 3 seconds, that's like even worse. So how do you actually make more complex constructs? How do you solve problems that are, take a longer time? Use coroutines. That's a scary word, but it's very, very, very easy. We're gonna see how the actual source code implementing that works, so just, brace for impact. So the normal function that we already saw, that bad function with the sleep, there, can be expressed as a coroutine by marking the function as being a coroutine and just yielding from a special sleep that is no longer this like blocking naive thing, but the sort of Async IO compatible way. But what is all this? I don't get it. So this coroutine function is a template. like a factory of coroutines. And when you execute it, like we actually call it, then it's a coroutine instance. It's a generator you then pull from it. So coroutine functions are like classes, and when you call a coroutine function, you get a coroutine. And then the event loop does things with the coroutine, like yields until stuff is done. So as I already told you, this async IO sleep thing is also a coroutine. So coroutines are basically composable. If you already are in one, you can call other coroutines with yield from. And then your code all looks like, it's sprinkled with yield from, but basically it reads linearly as if nothing ever happened. So yield from basically means await. That's no magic, just a generator. Let's see how it works. To schedule a coroutine, you have to create a task. Because otherwise, as I told you, the event loop is really simple. It only ever calls a callback and it's done. But if you create a task, by the way, if you do that, we're back in this concurrent land. If you create a task, then what you do is you create this special object that stores some state. And that special object in its very init method says, oh, hey loop, call me once, call just a single step, of that task later on. What does that mean? Well, a single step is really just calling a single step of iterating on that generator. Remember coroutines generators. So if we only ever call next, either we're pulling the next piece of computation or we get stop iteration, we're done. So we can set the result on a task and go away, or we get an exception, like shame on you on your rabbit holes and stuff. So then we just raise the thing. But if we're not done yet, if we just, pulled the next step and it's not done, what we do is we put the next step back in the event loop. So you can imagine if there are multiple tasks, each of them does only a little bit of work and then puts its next step, on the sort of queue to be executed on the event loop later on. So this is basically a series of yield, send, throw. That's very simple. So it looks sort of like this, We are done with, calling entire functions that are units of computation, but we have those little steps that as long as we are putting more of it on the event loop, which is done, transparently, we're good. But everybody lies, and I also lied. Our code has a terrible, terrible error in it. If you look really closely, we are telling the loop to stop after 2 seconds, but we also scheduled some tasks to take 4 seconds. I mean, wait, 3 seconds. So, they will not be done by the time we stop the entire loop. But Python async IO debug to the rescue. If you do that, it'll, warn you, hey, come on, I wasn't done yet. So you can actually notice that there was stuff that you had to wait for, but you didn't. So how do you make sure that the loop runs until a coroutine is complete? Well, you can use this sort of well-named method on the loop. So the loop can wait either on a coroutine or task. If you specify a coroutine, the task will be created implicitly for you, and then you're done. But what if you have more than one task that you want to wait for? Well, that's also easy. You just create all those tasks, or you get them from somewhere, doesn't matter. And then you run until complete one async IO wait, which, as you can imagine, is also a coroutine. But what it does is it'll wait until all of them are done. So synchronization, really easy. And now, I'm no longer lying. That's actually what happens. It's very nice, no warnings. It does what it has to do. But this entire code is a little naive, right? Like, we are doing computation that we later throw away. How would we actually get our results back? Maybe we need them. If we do, what we can do after waiting on coroutines to be, well, tasks to be done. On each of those tasks, we get this result method, which will basically give us the result back. That's sort of, I don't know, that wasn't explained too well, but what it does here is it'll put the date time on the example, like when we were first called, it'll wait, and then it'll return, you know, the date time of the time after waiting, right? So we can see, you know, at first it just goes bang, 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 and then it waits a little, you know. So this is what it does. If you only have one task, that's even easier. You can just use the value returned from run until complete. As I told you, like, you don't even have to create the task explicitly. You can just do this. That also works. But we fail. We go into rabbit holes, so we get exceptions. And how do we deal with exceptions? So not only results are stored in the task objects. If you get an exception, you can also get it after, receiving an exception during the call of a coroutine. So we can catch them. In our example, yes, we will just write whatever it was given, but when we try to sleep on G, well, we get a typer, and now we handled it sort of gracefully. As you would expect, if we are in this nice coroutine wonderland, we can also try and accept, you know, do stuff, do recovery, so that the event loop never ever notices that anything was wrong. That works. So once again, if you want to interact with coroutines outside of one, you have to either create a task or just run until complete, which you can do with coroutines directly. If you're already inside a coroutine, yes, you can still create tasks. Why not? That's only Python, right? But yield from is your friend. It makes code read really well. So use that. Like, create tasks means run asynchronously whenever the loop is running. There can be times where you aren't, right? But remember, a created task schedules its first step to be called soon on the loop, as we saw. Yield from means I'm waiting until this completes. So if you have a very complicated piece of code, you can still read it linearly. It will not go, you know, below that line until that coroutine is done. So because tasks are async, debug will complain if the result or exception is never read from, which is also nice. Isn't that debug well designed? I love it. So what's inside? Well, it's not twisted yet, so there's not entire internet with, you know, IRC, SMTP, or whatnot. There's not even HTTP at the moment. But we already can create connections which supports IPv4, v6, TCP, UDP, Unix sockets. We support SSL built in. It's nice. We can even resolve domain names asynchronously, which is good. We can also listen. We can be servers. We can be TCP and Unix socket servers. We can support SSL as well. UDP is supported, you know, as the same datagram endpoint as a client. So, you know, we are not really ever servers in UDP land, but yeah, like just to put it out there, you can also interact with UDP. Low-level APIs, like sort of socket thing, are also available. Unix pipes are also supported. Signal handling, supported, really nice. IO stream handling, supported. And some synchronization primitives. If you really love locks, you can have locks. You can have queues. But sometimes life is a bitch. And when it is, you get this third-party library, which is so cool, but it's blocking, and you can do nothing about it. So you execute it. No, not like this, but if you have this blocking thing, you can use an executor, which means you spawn a thread or a process and run this little piece of code there. But in your async wonderland, this is just treated as any other task. So executors live in concurrent futures. You can use them. You should use them. You will realistically use them. So you might just as well know about them. And even that very bad example stops being blocking when you use executors. There's two available, as I told you. You can either use the thread pool executor, which has less overhead, but you still have the GIL then, Or you can use the ProcessPool Executor, which means you pickle everything like crazy, but at least you don't have the guilt, so you can be truly concurrent at this point. So let me just finish by giving you some really random pieces of advice from implementing publisher-subscriber system in Async.io that is running now on like tens of thousands of MySQL servers at Facebook. Use Python 3.4. Yes, Async.io works with 3.3, but why would you want to deal with Python 3.3? Let alone the version for Python 2.7. You really don't want to do that. That doesn't work with yield from, that works with yield. But what that means is you get a performance hit from that. So why not? Like Python 3.4 is faster than 3.3. Debugging is much better. Garbage collection is smarter. And executors recognize dying processes. So that's really nice. Use them. Write unit tests. With async, it's much easier than with threads. You can even specify your very own event loop if you want. So you can mock out coroutines easily. You can run the event loop selectively. Like you don't have to wait forever. You can just run until complete on this small unit of code that you want to test. So I highly encourage you to do that. At least you know that the little blocks that you compose your big building of are valid. And also, set up debugging. Realistically, this is how you're going to develop your software, right? So those are the components that I put myself to, so when I'm coding. So Async.io starts being really verbose with logging. We also are really verbose about stuff that cannot be garbage collected. If you're running daemons, after a while, people will hunt you down like, why are you taking up so much memory on my database server? And so you might just as well learn about this very soon. The loop also has a debug switch, which makes some of the things run much slower, which is nice because it means that this implementation, like the coroutine implementation, is switched to one that is very verbose and tracks whether stuff is actually run or not. But also, it's slower, which means it's easier to see how stuff progresses, so you can like iterate over things easier. So yes, set debug true. Also, don't remember to close the loop. When you close the loop, if you are in the debug mode, Async.io will sort of tidy up and will warn you about all the things that you forgot to do. If you don't explicitly close it, yes, it will clean up, but it will not yell at you. And that thing, use it extensively, use it all the time. What if you forget to create a task for an instantiate coroutine? That's just one of the many examples of stuff that you will do if you start with Async.io. You just run it as any other function. You didn't put yield from there. If you use Python Async.io debug, it'll yell at you. It'll say, hey, you created this thing, and you probably wanted to run it at some point, but you never did. So I think my point is clear here, right? Just use that thing. But do not use stop iteration. That's a thing that people at the time of Python 2.3 did all the time. That was the only thing that we could do at the time. But now, raise stop iteration sort of confuses Async.io because generators and coroutines are implemented like the underlying implementation is the same. So don't do that. Just return. If you return, it's cleaner. It states intent better. You don't have to raise stop iteration anymore. I personally prefer ProcessPool Executors. They are a little slower at first, but they scale much more horizontally across your machine scores. So that's the correct answer, not the sort of simplest answer, but just use those. In Python 3.4, as I told you, if you have any of those child processes dying on you, well, the process pool will notice that and it'll yell at you too. So there's no undefined state anymore. It's pretty robust. But all in all, the docs are already pretty extensive, and as I hope I demonstrated, the implementation is pretty clear. So if there is stuff that works in a strange way and you don't recognize, like, I don't know, the trampoline implementation of the coroutine, which only calls a step at a time or whatnot, you can just dive in and read it. There is a reason why Guido implemented Async IO as the reference implementation. It doesn't do all the possible optimizations yet, but the intent was that the implementation is clean. So Twisted is a wonderful, wonderful piece of software, but the problem with it is that it has all the workarounds for the entire internet, which means, you know, good luck reading the deferred code base and understanding what it does. That's about it for my random pieces of advice. If you already used Async IO or you plan to use Async IO or you're afraid to use Async IO, ask me questions. But now, for something completely different. In Python 3.4, you have Async IO. It's awesome. If you sort of do refactoring, you know, you might lose the generator functionality of a coroutine if you don't put the @async IO coroutine, which is only sort of documentational and enables you to use debug, which you should. And also, support for asynchronous calls is here limited to only those expressions where you can put yield from. If you can't, like in for loops or context managers, well, bad luck, you cannot. So in Python 3.5, we're going to have PEP 492 implemented. I was already accepted. I was one of the reviewers, so I was really, you know, sort of, championing it. We get Async 08, like in Hack, like in C#, like in ES7. That's the sort of shared vocabulary people use thinking of async. So you no longer will have to use yield from. You can just say await, which is what it means. So that makes coroutines a native Python language feature, clearly separates them from generators, which is good. It removes the ambiguity and makes it possible to define coroutines reliably without reliance on a specific library. Like here, you use the asyncio.coroutine. With async being a part of the syntax, a part of Python, you no longer have to. But realistically, I wasn't showing you examples using that. You're likely not going to use this syntax soon, since the world wants to be compatible with older versions, like, for instance, what Red Hat supports or whatnot. So that's it. I'm pretty excited about this, but there's more things I'm excited about. So now for something completely different. Just 2 days ago, I was partying on a wedding of my sister. It's, hopefully the last. But type hints, a thing I was co-authoring with Guido and Yuka, was accepted. So yes, type hints are coming to Python. If you want to hear more about this, I'm gonna do a lightning talk about it. So yes, I used images in this presentation, and that's me. You can have this slide deck as PDF and ask me questions. Thank you very much.
Thank you for a great technical talk, Łukasz. Yep, and it's shared time. Okay, I can see some people over there.
Hi, I'm actually a Twisted user and a small-time contributor, so it resonates with me. Could you tell us a little bit more about error handling? Because I think this is the part that async frameworks in all of the languages get most wrong. So what happens if you schedule a call to be called, like you say, you tell the loop, call it in 3 seconds, and the thing it was told to call fails? How do you get the error back? How do you recover? How do you say, oh, if this actually finishes, then keep on working, and if not, then report an error?
One of the goals of Async IO was to have an asynchronous framework, like a vocabulary that you can use that is as close to normal programming. So like every coroutine is designed to be executed linearly. You can look at this one unit of code and not think about like all the other things that can possibly go wrong. You just evaluate the correctness of a single thing at a time. For instance here, like that's a good example since it has error handling right there. As long as you stay in coroutine land, which I encourage you to do, you just try and catch exceptions, like with any other framework, like in any other usage of Python. So this is what I would encourage you to do. I specifically didn't even mention futures, which are like deferreds from Twisted. They are part of Async IO, but in my usage of Async IO so far, I never had the need to use them directly. So they are a building block, and then error handling, yes, gets tricky because you have to do like set result, get exception, whatnot. But as long as you stay in coroutine land, you just have the flow of exceptions as you would expect it to behave normally. You can put PDB right there, and you can debug what's happening as if it was a blocking program.
Okay, so first thing, thank you. Great talk. Enjoyed it. Second thing, random remark. Async IO is that new. It hasn't that many batteries included, but it already has some ecosystem. So there is HTTP support somewhere. There are some web frameworks and other libraries and whatnot.
Well, so one of the design goals that Guido had with Async IO is to be sort of event loop agnostic. So there are already people using Async IO with the twisted event loop or with the tornado event loop, or the other way around, using tornado ready-made code with the Async IO event loop, or ready-made twisted code, which is awesome because they like implement everything. The problem with that is that this is still in the works, so it mostly works, but you will find issues with it. There are mostly being actively developed, but these are third-party libraries, so I would say yes, use them, but brace for impact. As for HTTP, there is AIO HTTP on PyPI that is mostly complete. The problem is that it's much slower than if you would use the twisted ones. That is sort of already optimized, but you can do that quite transparently already. Best part is that part of twisted works in Python 3, so there's nothing stopping you from doing that. Yeah.
Okay, last thing, fun stuff. What do you use it for in Facebook?
Yeah, so we use it for a number of things. For instance, we have this nice package distribution mechanism, which means if you have, so Facebook.com is this like big app. It gets deployed in one way, but there's multiple other smaller packages like publishers, subscribers, like I don't know, indexing servers. There's hundreds of them. They get distributed as packages. There's enough servers that it makes sense to just use BitTorrent to distribute them. And the BitTorrent clients that we're using are implemented in Python 3 with Async IO, and that actually, because that's much simpler than the blocking implementation we had before, that yielded us some performance improvements, even though in general you should not expect performance improvements, because very often you have computational heavy workloads, which means you have to sort of scale horizontally by running multiple processes. So that's one use case. And the other use case is we use Tau. Tau is the associations and objects. That's like a memcache fork that is right through. We ask if, I don't know, for a list of friends of Tomek, or am I a friend with another person? So we get this like nice object-oriented API with Tau, and Tau writes back to MySQL, behind our back. But we have multiple regions. So somebody has to invalidate the invalid data in those Tau instances in different regions. And that's done by Wormhole, a project I work on. Wormhole is implemented in C++. This has to be as fast as possible. But instantiating Wormhole instances and stopping them on MySQL machines is done by a daemon I wrote in Async IO in Python 3. So yeah, we're running Python 3 on like hundreds of thousands of machines at the moment, and very heavily on tens of thousands of them where it's performance critical, and without it, Facebook does not work.
Thanks for the talk. One question, I've heard a point of view that if you want to do something very efficient and stuff like that, why not use different languages instead of using coroutines and stuff like that? So what is your point of view in this manner?
Yeah, so as I told you, async programming is mostly, nice because it fits your brain. It requires you to sort of change your worldview a little, but once you do, it's very well, it reads very well, it tests very well, it self-documents really. So this is why you would want that. Performance comes with that sometimes. That depends on the workload. If you have a network-heavy workload, you will see that it's very nice. It maximizes a single thread. So if you run multiple processes, you will see, yes, this machine is overloaded now. I couldn't get it to this state before. Now I can, which is a good problem to have. But if you have a really CPU-heavy workload, I would encourage you to use NumPy, SciPy, maybe PyPy if you have lots of memory, or maybe a different language. Yes, we use multiple languages at Facebook too because of that reason. So I mean, there's no single silver bullet for everything. I prefer Async IO because it's clean. It produces code that is beautiful, and that's one of the biggest reasons we even use Python, right?
1 year ago, after the Twisted project, I was checking Async IO, and there was information that it can stay in Python 3, but can not stay 2. Is it stable now? It can be used in production environment. We've been sure that it will stay?
Async IO is pretty stable. I fixed a bug in it like 2 months ago, but there are gonna be like small bugs in sort of, startup shutdown or whatnot. But it's production ready. We use it in production and heavily at that. So I mean, we would not if it wasn't stable, but we use it on Python 3.4. The Python 2 version is, I think, like a proof of concept for stubborn people. Don't do that.
Yeah, but I was thinking this will be ready in Python 3.5, that it looked like for me that it will stay.
Yes, it will stay, definitely.
Okay,
yes.
Thank you.
Okay, thank you very much for the questions, and thank you very much for this extremely hot topic.